So thanks to the organizers for the possibility to speak to you today. I will talk about strong solutions to semi-linear SPDEs with unbounded diffusion. So since I guess SPDEs are not something that a lot of people work on, it seems to me in Paris, I will start with giving you a two-slide introduction to SPDEs. So the kind of SPDEs that I'm interested in, you can regard them as stochastic differential equations in infinite dimensions. So what do I mean by that? So you can consider this sort of very basic SDE, very well known. You have A, B constants, and you look for a process with values in R that satisfies this equation. And then I guess everybody knows that the solution to this is a geometric Brownian motion. And it's a basic exercise in stochastic calculus that you can show that this geometric Brownian motion satisfies this kind of equation. And in fact, you can show that, well, it's equivalent to saying that the process X satisfies this integral equation instead of satisfying this stochastic differential equation. So we'd like to take this as our starting point for the formulation of the same problem in infinite dimensions. And so what do I mean by infinite dimensions? So we would like to look at a process that takes values now not in R, but in a Hilbert space. Say just some general Hilbert space that's potentially infinite dimensional. So X will take values in the Hilbert space, and how should we now generalize our problem? So the real number A in this setting should become a linear operator that maps from the Hilbert space into the Hilbert space. We want to admit that A can also potentially be an unbounded operator, so think of the Laplacian. In the case it is an unbounded operator, however, we want to define exponentials, so we need to impose that A is the generator of a strongly continuous semigroup of operators. Our real number B should be replaced by some potentially nonlinear bounded operator. And okay, our Brownian motion, our one-dimensional Brownian motion should be replaced by something you call a cylindrical Brownian motion. So what is that? Essentially, say you have another Hilbert space U with some orthonormal basis, then a cylindrical Brownian motion heuristically is just putting an independent Brownian motion in each component of that Hilbert space. Now, there's a problem to that in that this is not a well-defined element of L2 of omega. So if you look at finite dimensions, so say you have an n-dimensional Brownian motion, then the n2 of omega norm of this thing would be n times t. So it blows up as the dimension goes to infinity. And you want to always have something in L2 of omega, right? When you think of stochastic calculus, you think of E to A symmetry, so you want to have your objects to be well-defined in L2 of omega. However, what you can do is you can nonetheless define a stochastic integral with respect to this ill-defined quantity, given that your integrand is somehow regularizing. And what do I mean by regularizing? So say you look at a bounded operator from your Hilbert space U to H. You take an orthonormal basis f of H, and say you have this kind of decomposition. So for simplicity, think of U and H being the same space, and then this is basically an eigenvalue decomposition. So the lambda k's are the eigenvalues, so to say. And if now you admit that the sequence of eigenvalues actually lives in small L2, then this is what we call a Hilbert-Schmidt operator from U to H, which is denoted by L small 2 of U to H. Then, well, okay, you compute the stochastic integral with respect to this constant operator. What you get is, well, this expression. So you just have the increments of your independent Brownian motions. You compute the sum, and given that the sequence of eigenvalues is in L2, you have the convergence of this sum. So essentially what this means is even though your W2, your cylindrical Brownian motion, is not well defined as an object in L2 of omega taking values in U, you can basically define a stochastic integral provided that your integrand takes values in the space of Hilbert-Schmidt operators. So this is basically a bit the short story. So you can generalize this to stochastic processes taking values in Hilbert-Schmidt operators that have good integrability properties, and then you have E to isometry, and you have a stochastic calculus at hand. So given all this, how do we set out our problem? What do we want to consider as a solution to the stochastic partial differential equation? So we consider a Hilbert space again, so where our stochastic process is supposed to take values in. We take A, which is a generator of a strongly continuous semigroup. We take B, which maps from the Hilbert space to the space of Hilbert-Schmidt operators, which we need in order to have a well-defined stochastic integral. We have the cylindrical Wiener process, and then we call a progressively measurable process U a mild solution to this equation, provided that P almost surely we have as an equality in H this expression. So this is basically the analog of what you saw here in a geometric Brownian motion, the one-dimensional sense, where basically we just replaced all one-dimensional objects by their corresponding infinite-dimensional object. What is very nice about this formulation? Well, first of all, you have the unbounded operator A doesn't appear here anymore, so you have the semi-group, which is regularizing, which is a bounded operator. It's better than the Laplacian, for example, which would be unbounded. And in particular, this has the form of a fixed point problem, right? So if you have a process and you define this to be your operator K, essentially what a mild solution is a fixed point of this operator K, abstractly speaking. So what you need is somehow a possibility to show that K is a contraction on a suitable Banach space, to use your Banach fixed point theorem to conclude the existence of a unique mild solution. And the main tool for doing that is to prove a maximal inequality for these expressions, which you call stochastic convolutions. So if provided your process lives in LP of omega, L infinity of 0t, and taking values in H, which is a space that will reappear all the time, then you can basically bound the stochastic convolution in the norm of this Banach space to the power p, which is essentially written here, by c times t to the p half times the expectation of, well, this expression here. So what is very nice about this expression? Well, provided that your operator B mapping from the Hilbert space into the space of Hilbert-Schmidt operators is now of, say, some linear growth and also Lipschitz, then you see that this, so think of B now to be Lipschitz, think of the difference, then you use the Lipschitz continuity into the space H, so you have this norm appearing on the other side, so you have that your operator K becomes a Lipschitz continuous operator with a Lipschitz content that depends on the time horizon. So basically, by choosing the time horizon sufficiently small, you get that K is a contraction, and therefore, by Banach's fixed point theorem, you have a unique mild solution in this space. And you can show that it's also continuous. So this is basically the classical setup, and what I'm personally interested in now is a problem where you have an additional unbounded operator in front of the diffusion, which is supposed to be the fractional power of the generator over here. So take a Laplacian to make it more readable. So minus the Laplacian is a positive operator, so I can take the root of it. And as a mild formulation, accordingly, I want to consider this problem. Now, I cannot use this maximal inequality from before because that required the B to take values in the space of Hilbert-Schmidt operators. So in particular, the diffusion needs to be bounded, which is not the case because, well, here is an unbounded operator. However, the semi-group gives me some regularity. So if I apply first the semi-group and then the fractional power of the generator of that semi-group, I get a bounded operator. And Hilbert-Schmidt operators, they basically form an ideal in the space of bounded operators, which is a fancy way of saying that a bounded operator composed with a Hilbert-Schmidt operator is Hilbert-Schmidt. So this is still a well-defined stochastic integral. But in order to find mild solutions to this, you need to find a generalization to the maximal inequality over here. And so what can you do? You have basically the same setup. You still have your B, which maps from H to the space of Hilbert-Schmidt operators, and we impose a certain growth condition. And provided that is the case, then for all delta, I forgot to mention it's between 0 and strictly smaller than 1. And for a P that is sufficiently large, then we have for all progressively measurable processes that live in the space the following generalization of the maximal inequality. So we have this unboundedness appearing. So again, think of A as a Laplacian with the fractional power here. And we basically have to pay for this unboundedness by losing some of the control we have here on the time horizon. So instead of t to the power p half, we now have only p to the power p half times 1 minus delta. So we lose a bit of control, but nonetheless, the qualitative behavior stays the same. We have some kind of control on the time horizon. So if we choose the time horizon sufficiently small, we get again a contraction and therefore a solution. So yeah, what is the corresponding theorem? So you look at your SPDE and you set up the mild formulation. Then you have a unique fixed point to this operator K, which means you have a unique mild solution that is also almost surely continuous in time. And OK, so for once I will write how this works. So you look at this operator K, and well, at this step you get that, and you use the maximal inequality from this line to the next. You see that you have the 1 minus delta appearing. And okay, I forgot to mention, you need to admit that B admits the growth condition that we stated, and that B is Lipschitz as an operator from H to the space of Hilbert-Schmidt operators. And in this case, well, what we recover is here again the norm in this Banach space. So if we take the p root and we choose t sufficiently small, k becomes a contraction, and we have the mild solution. Now, okay, this is all very abstract, okay, so the B is a diffusion that goes from some Hilbert space into the space of Hilbert-Schmidt operators from a Hilbert space to another Hilbert space. So what does it mean in the real life? So say we are giving a problem where we have only finite dimensional noise. So we have a d-dimensional Brownian motion, and the term in front of the fractional Laplacian is just a sum of some functions bi. And your u's, they're supposed to take values in the Hilbert space, which in our case is supposed to be L2. So the problem now becomes, given you have some functions that map from R to R, under what condition is the associated operator here a well-defined operator which is Lipschitz and satisfying the growth conditions that we need? So this is what you call a Nemitsky operator, associated to a function which goes from R to R. So you see, we're given some functions that map from R to R, and we ask ourselves, we have an associated operator that is supposed to map from a Hilbert space into the space of Hilbert-Schmidt operators. Under what conditions on these functions R is the associated operator possessing the good properties? And well, that's a lemma that you can, basically the main idea is found in the first publication of Martina Hofmanova. You take a d-dimensional Hilbert space, as I said already, you have a d-dimensional, you have d functions B1 for BD, and they're supposed to be C1 end of bounded derivative that also satisfy this growth condition, which is, as an inequality in R, well, BI takes values in R, and Xi is also R. If we have these conditions, then the associated Nemitsky operator, now seen as an operator mapping from L2 into the space of Hilbert-Schmidt operators, so this thing down here, satisfies the growth condition, it's well defined, and it's Lipschitz. So what we can do is we can apply our theorem, and we have existence and uniqueness of a mild solution, as said before. Now the thing about mild solutions is that they're very weak solution constant. They're even weaker than weak solutions. So how can we get more regularity now afterwards? So one idea would be to, well, we have basically set up this thing in the space of L2. So we could ask ourselves, can we do the same argument in Sobolev spaces of high enough order, and then use the embedding theorem to say that, well, my process takes values in the space of differentiable functions. So this would be an idea, but the problem is, as soon as you consider Sobolev spaces, you have the derivatives intervening, so what you necessarily lose on the level of Nemitsky operators is continuity. So, I mean, you have no possibility to recover Lipschitz continuity, so there's no way to set up a fixed point argument for that. Instead, what you can do is, well, you know that you have a unique solution in L2, so you can consider the associated sequence of Picard iterations. You know that they converge strongly in the space, well, ZL2, as I mentioned, this space I mentioned before. And you can now look at the sequence of Picard iterations, provided you have some bounds. So provided we have some growth conditions on the Nemitsky operators, which you can do in Sobolev spaces, you can look at the sequence of Picard iterations and basically look at the sequence of Picard iterations in the Sobolev space and derive a uniform bound on the sequence of Picard iterations. By deriving a uniform bound on the sequence of Picard iterations, basically what you do is you say that by Banach-Alaoglu you have a weak star convergence subsequence, which converges to a limit that obviously needs to belong to the associated space of processes taking values in the Sobolev space. And then what you use is a uniqueness of limit argument to say that actually, provided my initial condition was already smooth or in the Sobolev space, then the solution I constructed in L2 actually stays in the Sobolev space. So, I mean, maybe. So what I mean is, so you have your L2 space, you have your Sobolev space, you have your sequence of Picard iterations, and provided that you start in the Sobolev space, by having a uniform bound on the norm of Picard iterations in the Sobolev space, you say that the limit that exists in L2, it actually needs to stay inside the Sobolev space. So by which you can conclude that actually the solution you constructed doesn't only belong to L2, but actually to the Sobolev space. And then you can play the same game with, well, some generalizations. You need to work in Banach spaces and you need to use some inequalities. But then you can play the same game for Sobolev spaces of arbitrary order. And this way you can deduce that actually the mild solutions you constructed are differentiable, which is the same as saying that actually you have strong solutions. And that's what I wanted to tell you.
Thank you, Florian. Are there any questions, comments?
So you basically take an unbounded drift in a way, but it's still connected to the operator that acts on the, let's say, on your leg. Is there a way to extend this result to other operators which are not being fitted?
Yeah. So the problem is that, well, there's, well, everything basically relies on this maximal inequality, which, I mean, I stated it in a Hilbert space, but you can prove it in a Banach space where you have to work with two smooth Banach spaces. And then in the end, I mean, what you kind of use is a certain inequality, looks a bit like that, well, yeah, if A is a generator and you take a power and you apply the semi-group, then this is a bounded operator, so this is the operator norm by 1 over T power delta. So and this is due because this is exactly the generator of the semi-group. Now, what you can do is, if you have a different operator which is unbounded in front, sometimes what you can do is you can sort of insert the fractional power of the generator with its inverse and then play a game with that. So this is basically what Hoffmanova does, because she considers the problem with an unbounded drift, not an unbounded diffusion. And this is basically what she does. So she considers this problem. So here you have another unbounded operator. And what you can do is basically, if you set up your mild formulation, you insert here the inverse of a fractional Laplacian and the fractional Laplacian here. And so now what you can do, okay, here you can do the standard game. And basically the unboundedness of this divergence is eaten up by the inverse of the Laplacian. So this actually becomes a bounded operator that is also Lipschitz in the good space. So you can do the same argument. So what you can do is, I mean, yeah, you still need to exploit kind of this inequality. There's no way of generalizing, I think, the maximal inequality this way. But provided you have this unbounded operator that you can sort of kill with the inverse power of the generator here, you can still get nice results. But the problem, yeah, for me, like in the beginning, my hope was that I could do the same trick in the diffusion term. But the problem is, if you think about it, so this would be this problem. If you think about it, basically here we gain, say you're in a Fourier basis, so u in L2 of the torus or of 0, 1, whatever, you have a Fourier basis of sine kx and cosine kx, maybe times the scale. What you get here is a minus k squared. So a minus k is something damping, right? So exponential of minus k squared. And here this is potentially, say the b is linear, this is potentially blowing up because you have minus a Laplacian, so here you have positive eigenvalues. So this would be, you would gain a k here. But the problem is that, well, you're in Ito calculus setting, so the quadratic variation of this term would be plus k squared, which basically kills the minus k squared on this side. So you cannot really work with with this trick. So you need to use another thing. But I didn't have time for that today.
Any other question? So then I think let's thank Florian again.
Okay.